students, good afternoon. So in the morning session, we discussed about circular birefringence, circular dichroism, cotton effect, and ORT curves and octane rule. So next continuation in ORT, that is optical rotatory dispersion, application of octane rule. And next, we will discuss about axial alpha haloketone rule. So, I am audible?
Yes, sir.
Okay, fine. So, in the morning session, we discussed about cotton effect and octane rule, right? And circular birefringence and circular dichroism and cotton effect and ORT curves. So, listen, applications of octane rules. Octane rule. So, listen once again, octane rule. So, here in octane rule, the upper left and lower right substrate contributes the positive cotton effect, and the substrates in upper right and lower left contributes the negative cotton effect. So in cyclohexanone, C3 and C6 contributes a negative cotton effect, and C2 and C5 contributes a positive cotton effect. So your C2, C6. So this is C2, lower right, and C5, lower left, sorry, C6. So the C2, C6, sorry, C2, C5 contributes the positive charge, and C3, C6 contributes the negative charge. So see the next continuation, applications of octane rule. Applications of octane rule. So example. So by using octane rule, we can know the configuration and confirmation also. So see an example. Plus or minus 3-methyl cyclohexanone. So this is plus 3-methyl cyclohexanone is known to have R configuration. It is known to have R configuration. So see the structure of 3-methyl cyclohexanone. 3-methyl cyclohexanone. C double bond to 3-methyl cyclohexanone. So this is R configuration. So R 3-methyl cyclohexanone. Cyclohexanone. See the chain conformation of cyclohexanone. CH3 H C double bond, or upon interconversion C double bond O keto group, CH3 H or M. Simply recognize. CH3 C double bond O. The chair confirmation of cyclohexanone, 3-methyl cyclohexanone. So see, so this is first carbon, second carbon, third carbon. First carbon, second carbon, third carbon. 1, 2, 3, 4, 5, 6. Here 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. You see, C double bond O, C2, C3, C4, C5, C6, 6 carbon. This C double bond O. So at third position, on a hydrogen, right? Hydrogen present at axial position. Here, CH3, right? Equatorial position. This is a 3-methyl cyclohexanone. So what is the sign of this 3-methyl cyclohexanone according to octane rule? According to octane rule. So this is upper right. C5 is upper right and C3 is the upper left. Upper left. Upper left and it is upper right. So according to octane rule, upper left, the substance in upper left and lower right contributes towards positive Cotton effect. So the substance in upper left contributes positive Cotton effect. So therefore, positive Cotton effect. Positive Cotton effect. Clear. So it is methyl at equatorial position. So methyl at equatorial positions, it gives a positive Cotton effect. Positive Cotton effect. Next, take a screenshot and go to the next slide. So 3-methyl cyclohexanone. So methyl group at axial position here shows positive Cotton effect. Suppose C double bond O, second carbon, C3 third carbon, C4 fourth carbon, and C5, C6. So it methyl group at axial position, CS, and hydrogen at equatorial positions. So in this case, so this is upper right. So the methyl substrate is upper right. So according to octane rule, upper right, the substance in upper right contributes a negative Cotton effect. Negative Cotton effect. So therefore, negative charge. Negative Cotton effect. If methyl group present at axial position, it gives a negative Cotton effect. In case of methyl at equatorial position, it shows a positive Cotton effect. So this is one of the example for application of octane rule. Next, Another example, confirmation of benthone. Confirmation of benthone. Confirmation of benthone. Structure. Double bond group. That's occupied group. Orbital. So first carbon, second, third, fourth, fifth, sixth. So see here. Show here the isopropyl group at the equatorial position and C2. First of all, C double bond O, C2, C3, C4, C5, C6. So one metallic group at C5 position and an isopropyl group at C2 position. So here, according to octane rule, so this is upper right, upper left, lower right, lower left. So according to octane rule, so here upper left and lower right contributes towards positive Cartan effect, and upper right and lower left negative Cartan effect. So therefore, here upper left positive, negative, negative, positive. So it's C2 position, lower right. So it is positive, positive Cartan effect. If the substrate at C2 present at equatorial position, which shows positive Cartan effect. The substrate at equatorial position shows positive Cartan effect. So in case of C5, C4, so C2, C3, C4, C5, C6. So the substrate presented axial position. The substrate presented axial position. So this is a lower left. Lower left. So lower left. Lower left. According to octane, lower left is contributes a negative Cartan effect. Therefore, negative Cartan effect. These are the applications of octane rule. 3-methyl cyclohexanone and benthone. This is about octane rule and applications of octane rule. Next last topic, that is axial alpha halo group ketone rule. Axial alpha halo ketone rule. Axial alpha halo ketone rule. So this rule is applied when there is an axial halogen. Like chlorine, bromine, iodine. So this axial haloketone rule applied when there is an axial halogen group, like chlorine, bromine, iodine, to keto group of cyclohexanone molecule. Suppose, so according to axial alpha haloketone rule, suppose if the halogen appears to the right side of the carbonyl group, the halogen appears to the right side of the carbonyl group, so the compound will show positive Cartan effect. So right side of the carbonyl group, the compound will show positive Cartan effect. So if the halogen appears to the right side to the carbonyl group, the compound will show the positive Cartan effect. Suppose in case of, if it is to the left side, if it is to the left side, left side of the carbonyl group will show negative Cartan effect. Negative Cartan effect. So if halogen right side to the carbonyl group, it shows the positive Cartan effect. Or if it is to the left side of the carbonyl group, it will show negative Cartan effect. Negative Cartan effect. So positive right side will show positive Cartan effect. Halogen group left side will show negative Cartan effect. One example. Sorry. Suitable bond. Here, alpha halo, axial alpha halogen. So here, view from this side. So here, the halogen is presented right side to the keto group or carbonyl group. So it shows this effect, right side to the carbonyl group. Halogen presented right side to the carbonyl group will show positive Cotton effect. Positive Cotton effect. Suppose in case of sorry, so here from this side. So here the halogen, axial alpha halogen, is left side to the carbonyl group. So we will show negative Cotton effect. Negative Cotton effect. So this is about axial halo ketone group. Axial halo ketone group. Next, applications of axial halo ketone group. Applications of axial halo ketone group. Fluorination of 3-methyl cyclohexanone. So applications of application. Applications. So 3-methyl cyclohexanone upon chlorination. Upon chlorination. So it can form 2-chloro-5-methyl cyclohexanone. 2-chloro-5-methyl cyclohexanone. So see, chlorination of 3-methyl cyclohexanone. Chlorination of 3-methyl cyclohexanone. So, 3-methyl cyclohexanone upon chlorination. Upon chlorination, so it can form 2-chloro-5-methyl cyclohexanone. Chloro 5-methyl CH3 here and carbonate P2. So here this is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 2-chloro-5-methyl cyclohexanone. So this is the 2-chloro-5-methyl cyclohexanone. So this 2-chloro-5-methyl cyclohexanone. So here the halogen presented left side to the keto group. So according to alpha halogen, so if halogen presented left side to the carbonyl group will show negative Cotton effect. Negative Cotton effect. Therefore, will show negative cotton effect. Negative cotton effect. Otherwise, the molecule upon interconversions rotation will form this configuration CH2 equivalent position. So methyl equivalent position. So upon chlorination, same. Upon chlorination, so it can form same 2-chloro-5-methyl cyclohexanone. Two chloro 5-methyl cyclohexanone. So chlorinate axial position and here methyl equivalent position. This is the 2-chloro same 5-methyl cyclohexanone. So here from this side, the alpha halogen presented right side to the carbonyl group. Here, this halogen group presented right side to the carbonyl group. So we'll show positive cotton effect. We'll show positive cotton effect. Positive cotton effect. So this is the chlorination of 3-methyl cyclohexanone. So chlorination of 3-methyl cyclohexanone. So see another example. So trans 1 decalone. So trans decalone. Trans decalone. So bromination of this trans decalone. So in chair form. Hydrogen, and C double bond 4. So upon bromination, so it can form 2-bromo derivative. 2-bromo derivative. Carbonyl group, keto group isostates, and here 2-bromo derivative. 2-bromo derivative. So here this is trans decalone upon bromination can form 2-bromo derivative. So this 2-bromo derivative shows which effect according to alpha haloketone group. So here the halo group presented right side to the keto group. Right side to the keto group. So we'll show positive cotton effect. So we'll show positive cotton effect. Positive cotton effect. Next. Okay, so this is the 9s10r configuration here. So this is 9s10r configuration. Suppose about the group, right? Carbon. So this is the first carbon. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 9 or 10s configuration. So this is 9s10. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 9 is 10 or configuration and will show positive cotton effect. So in case of 9 or 10 is configuration. See, share confirmation. Hydrogen, 9, 10 positions, and here keto. So this 9 or 10 is decalone upon bromination. On bromination, it can form 2-bromo derivative. 2-bromo derivative. Hydrogen, and carbon and that is ketone, and here bromine. So this is a 2-bromo derivative. So this 2-bromo derivative so shows which effect here. The axial halo group presented left side to the keto group. So according to the axial halo ketone group, so it shows negative cotton effect. Negative cotton effect. So this is about axial halo ketone group. Axial halo ketone. This is about ORD. ORD. So see, listen once again. Axial alpha halo ketone rule. So this rule is applied when there is an axial halogen is present. Axial halogen to keto group of cyclohexanone. So this rule is applicable when there is an axial halogen like chlorine, bromine, iodine to keto group of cyclohexanone. So if the halogen appears to the right side of the carbonyl group, the compound will show positive cotton effect. If the halogen appears to the right side of the carbonyl group, the compound will show positive cotton effect. Suppose if it is to the left side of the carbonyl group, will show negative cotton effect. Negative cotton effect. So if the halogen appears to the right side to the carbonyl group, it shows positive cotton effect. So suppose if it is a left side of the carbonyl group, will show negative cotton effect. So example is so this alpha halo ketone cyclohexanone. So the cyclohexane view from this side. So right side to the carbonyl group. So will show positive cotton effect. So this axial position. So from this view, so the axial alpha halo group present at the left side to the carbonyl group. So will show negative cotton effect. Negative cotton effect. You see the applications of axial halo ketone group. So first one, chlorination of 3-methyl cyclohexanone or 3-methyl cyclohexanone. So chlorination of 3-methyl cyclohexanone to gives 2-chloro-5-methyl cyclohexanone. 2-chloro-5-methyl cyclohexanone. So here, this is the 3-methyl cyclohexanone upon chlorination. So we will form 2-chloro-5-methyl cyclohexanone. So in this 2-chloro-5-methyl cyclohexanone, a chlorine present at alpha position and axial position. This is the alpha halo, axial halo group. So this axial halo group present at left side to the keto group. From this side, so left side to the keto group or carbonyl group. So we'll show negative cotton effect. Negative cotton effect. Suppose here, so this chair conformation or configuration upon chlorination. So it can form same 2-chloro-5-methyl cyclohexanone. So in this 2-chloro-5-methyl cyclohexanone, so this chlorine halo group present at alpha position, axial position, and it is right side to the carbonyl group. So according to axial halo ketone rule, the halo group present at right side to the carbonyl group will show positive cotton effect. Positive cotton effect. So last example, that is a 9s10r. So this is a 1, 2, start 4, 5, 6, 7, 8, and 9. This is a trans decalone, trans 1 decalone. So this trans 1 decalone upon bromination, trans 1 decalone upon bromination, it can form 2 bromo derivatives. So the bromine present at axial position, and this bromine present to the right side to the carbonyl group. So in 2 bromo derivative, so the bromine present at axial position, that is alpha position, and it is right side to the carbonyl group. So according to alpha halo axial ketone rule, so if the halogen appears to the right side of the carbonyl group, the molecule or the compound will show positive cotton effect. Therefore, it shows positive cotton effect. Suppose in case of 9R 10S configuration, so this trans decalone, 1 decalone, 9R, so this 1, 2, 3, 4, 5, 6, 7, 8, this is 9 and 10. 9R 10S trans decalone upon bromination. So it can form same 2 bromo derivative. And these bromine at axial position, present at axial position, and it present to the left side to the carbonyl group. Left side to the carbonyl group. So we'll show negative cotton effect. Negative cotton effect. So this is about axial halo ketone group. Axial haloketone rule and applications of axial haloketone rule. So this is about ORT, optical rotatory dispersion, ORT. See, so listen, octane rule again, once again, octane rule. So this octane rule, what is octane rule? And it is elaborated by Moffitt and Woodward Moskowitz. Second. Octane rule. So we already discussed in the morning session octane rule. So just again. So this it is an empirical rule and it was elaborated by Moffitt, Woodward, Moskowitz, Klein and Desiree. So in 1961. So this rule permits the prediction of the sign of the cotton effect for optically active cyclohexanones. So sign of the cotton effect for the optically active cyclohexanones from their structure, configuration and conformation. So to apply the rule, so here the carbonyl group should occupy the head of the chair or board conformation. So the carbonyl group should occupy head of the chair. And the system is viewed along the C double bond O bond. C double bond O bond. And next, the cyclohexanone system oriented in 3D coordinated system. That is a three-dimensional coordinated system. So see the structure of a 3D diagram of cyclohexanone. So here the three orthogonal planes divide the molecule into 8 octanes or 8 sectors. First one. So a vertical plane A. So passes through the carbonyl oxygen. See here, plane A. So this is a plane A, right? So this is a plane A. Vertical plane A passes through the carbonyl oxygen. Carbonyl oxygen, that is C1. And next, C4. So a vertical plane A passes through the carbonyl oxygen, that is C1 and C4. So both axial and equatorial bonds on C4 lie in the same plane. So both axial and equatorial bonds on C4 lie in this plane. So next, horizontal plane B. So this is the plane B. So horizontal plane B. Passes through the carbonyl oxygen, that is C1, C2 and C6. It passes through the C1, C6, C2. So here equatorial bonds on C2 and C6 are almost in this plane. Equatorial bonds on C2 and C6 are almost in this plane. And next last one, another plane, that is C. So it can bisect the carbonyl group, carbonyl bond. It can bisect the carbonyl bond. So here these 8 octanes are obtained, which are divided into 2 sets. These 8 octanes are sectors divided into 2 sets. So first one, front front octanes or 4 front octanes or 4 rear octanes. First one, 4 front octanes. Second one, 4 rear octanes. So front octanes also called as are near to the observer, and rear are far octanes away from the observer. So here the 4 front octanes are usually empty. The front 4 octanes are empty. So therefore, they may be ignored. They may be ignored. And next, the rear 4 octanes are designated as, okay. So the rear 4 octanes are designated as lower right, lower left, upper right, upper left. So lower right LR, lower left LL, upper right UR, and upper left UL. So here the substituents in upper left and lower right contributes positive Cartan effect, and the substituents in upper right and lower left contributes negative Cartan effect. Negative Cartan effect. So see the structure of cyclohexanone. So I'm taking a cyclohexanone. So this is C1 carbon. So this is C1 carbon, C2, C3, C4, C5, C6, cyclohexanone. So from this view, so this is upper right. This is the upper right, right? Upper left. So left side to the carbonyl group, right side to the carbonyl group, and the upside, upper right and upper left. C5 is upper left, and C6. So it is the lower side. The double bond group. This is the upper left, upper right, lower left, lower right. So C6 lower left and C2 lower right. So here, according to the octane rule, the substituents in upper left and lower right contributes the positive Cartan effect, and the substituents in upper right and lower left contributes negative Cartan. Therefore, upper right negative, upper left positive, lower left negative, and lower right positive. So see the in chair confirmation of the molecule. So at C3 and C4, substituent at C3 and C4, substituents at C3 and C6, sorry, substituent at C3 and C6 will show negative Cartan effect. So C3, where is C3? So here, C3, C3 and C6. So C3 is upper right and C6 is a lower left. So upper right and lower left will give the negative Cartan effect. So therefore the substituent at C3 and C6 will show the negative Cartan effect. And the substituent in C2 and C5 will show positive Cartan effect. C2 and C5. So where is C2? Here C2 and C5. The substituents at C2 and C5. What is C2? Lower right. And what is C5? Upper left. So lower left, lower right will show positive Cartan effect. So therefore, the substituent at C2, C5 will show positive Cartan effect. So this is about octane rule, octane rule. And see the applications. So applications of octane rule. So this 3-methyl cyclohexanone. So 3-methyl cyclohexanone. Suppose the methyl presented, suppose your left side here. So it is upper left. Upper left means positive carbon effect. Suppose in case of, I'm taking this side, first one, axial position, and next I'm taking this equatorial position, C3 methylate equatorial position. Next C3 methylate axial position. This is axial position, and here this is equatorial position. So when methylate equatorial position, it shows positive carbon effect because it upper left, it shows positive carbon effect. In case of methylate axial, this is upper C double bond O group. This is upper right, upper left, lower right. So upper right means negative carbon effect. Negative carbon effect. So next example, conformation of benthone. Same is so it also the methylate equatorial position. So this upper left positive charge, upper right negative charge, and C2, the isopropyl group presented C2. So it is lower right. So lower right shows positive carbon effect at equatorial position. So in case of it is in axial position, it is lower left. It shows negative carbon effect. So this is about octane rule and applications of octane rule. So this is about ORT. So is there any doubt in ORT? CP, CD, CE, Wardicals, octane rule, applications, and axial alpha-ketone rule. So this is enough for today, and remaining the next class. So take the screenshots of all slides. So this is about ORT. So you can leave from the meeting, everyone. So optical laboratory, this person is completed. So remaining the next class. So this is enough for today. Remaining the next class. So you can leave, everyone. Sir, meeting end, sir.